everyone. So the term that I was given for the study guide was Dalton's Law. And so Dalton's Law states that each gas exerts its own pressure, and the total pressure of a gas mixture is the sum of the pressure of the individual gases. And this is important for respiration, because it's actually not the percentage of oxygen that matters, it's a partial pressure of oxygen. So it's not a straight percentage of oxygen across the board that you need to sustain life. It depends on what type of atmosphere you're in, if you're up on a mountain, if you're at sea level, or if you're underwater. That all depends, and it will make a difference with how much oxygen is actually needed to sustain life. So partial pressure is created by timesing the amount of any type of gas by the pressure that it's at. So this is a look at what the partial pressures of the different components of air are at sea level. So at sea level, oxygen has a partial pressure of about 160 millimeters of mercury. Nitrogen has a partial pressure of about 600 millimeters of mercury, and carbon dioxide has a pressure of about 0.3 millimeters of mercury. So the total pressure of air is approximately 760.3 millimeters of mercury. Hey everyone, the topic I was given was Dalton's Law. And Dalton's Law states that each gas exerts its own pressure, and the total pressure of a gas mixture is the sum of the pressure of the individual gases. So for air is 21% oxygen, 79% nitrogen, and 0.4% carbon dioxide. So the partial pressure of each of these at sea level would be, so for oxygen, it would be 160 millimeters of mercury. For nitrogen, it would be 600 millimeters of mercury. And for carbon dioxide, it would be 0.3 millimeters of mercury. So the total pressure of air is approximately 760.3 millimeters of mercury. So total pressure and partial pressure are important for respiration because it's actually not the percentage of oxygen that matters. It's a partial pressure of oxygen that matters for human survival. Depending on what type of atmosphere you're in, if you're, say, up on the top of a mountain, at sea level, or scuba diving underwater, the pressure is what affects the percentage of oxygen that your body needs to survive. And it's 122 millimeters of mercury is the amount of oxygen. Professor Langston gave us this diagram, PP over percentage TP. So it's partial pressure, percentage, and total pressure. So if you're looking for the percentage, you would put your thumb on the percentage, and that will give you the partial pressure divided by the total pressure. So if we were trying to calculate what the minimum amount of oxygen needed to survive at sea level would be, we would take 122, which again is the set point, which is the least amount of pressure of oxygen a human needs to survive. You would divide it by 760, which is 1 atmospheric pressure, which is what we would be at sea level, and we would come up with 16% oxygen. Whereas if we were diving and we were at 10 atmospheric pressures, about 7,600 millimeters of mercury, if you were to divide that by 122, we would come up with 1.6% oxygen needed. And then if we were up in a plane and the plane became depressurized, it would be at 222 millimeters of mercury if you were at 30,000 feet. So it would be 122 divided by 222, which comes up to approximately 55% oxygen needed. So this is a way to determine how much oxygen we would need at any given point. So it's a good rule of thumb to just remember that as atmospheric pressure increases, oxygen levels decrease. And as atmospheric pressure decreases, the level of oxygen increases. So it's just the opposite. When one increases, the other decreases, and when one decreases, the other increases.